Okay, let's talk about the most fundamental concept in chemistry, the atom. Now the reason why the atom is the most fundamental concept is because all of the rest of chemistry is based off it. Chemistry is the study of matter, and without atoms we wouldn't have any matter, and matter is composed of atoms. So what is an atom? Well, an atom is composed of two main parts. It's composed of the nucleus and the electrons. So in the nucleus we have protons and we have neutrons. And then in the electrons we have, of course, electrons. Now these three subatomic particles have different properties. They have different masses and different charges, so they weigh different amounts and they each have a different charge. And we can summarize these in a table. So if we get out the green, we can draw a table. That was really neat. I'm quite proud of that. So we have the protons, we have the neutrons, and we have the electrons. Now we're going to list their masses, measured in kilograms. Kind of big for such a tiny particle, but that's the way it's done standardly. And we're going to measure its charge in a unit called coulombs. If you do physics, you'll be familiar with that. So the proton has a mass, of 1.672 times 10 to the power of minus 27. Now this should blow you away as being such a small number. In fact, that is such a small number that it barely exists. If that was a unit of measurement in meters, like if we had 1.672 times 10 to the power of minus 27 meters, that is almost an impossible length, which wouldn't matter, because nothing is that size. So let's go on to look at the mass of the neutron. Similarly, it has a mass of 1.674 times 10 to the power of minus 27. This is slightly more than the proton because of some physics that I'm not going to go into here. And the electron has an even tinier mass of 9.109 times 10 to the power of minus 31 kilograms. So already we're getting into some pretty hard to deal with numbers here. Then let's go on to look at charges. The proton has a charge associated with it as positive 1.602 times 10 to the power of minus 19. A little more bearable than these incredibly small numbers, but not by much. So then the neutron, handily, has a charge of 0. It has no charge associated with it. And then the electron has a charge of minus 1.602 times 10 to the power of minus 19. Now, you're not going to be expected to know these values because they're very complicated. So instead what they do is simplify these by creating something that we call the relative mass and the relative charge. So you might be able to point out that these two values here, these masses, are quite similar, and that these two charges definitely are similar. They're just the negative and positive form of the same thing. So let's try and figure out how we can simplify this. Well, if we divide the mass of the proton by itself, so 1.672 times 10 to the power of minus 27 by 1.672 times 10 to the power of minus 27, we get an answer of 1. So we can say that the proton has a mass relative to itself of 1. And we can do the same with the neutron. If we get the neutron and divide the mass of the neutron, 1.674 times 10 to the power of minus 27 by the mass of a proton, 1.672 times 10 to the power of minus 27. We don't get an answer exactly equal to 1, but we get an answer close enough to 1 that it doesn't matter. So we call this 1 and this 1. Well, this is approximately equal to 1. So then if we do the same with the electron, we can divide 9.109 times 10 to the power of minus 31 by the mass of a proton, which is 1.672 times 10 to the power of minus 27, we get an answer equal to 1 over 1,836. Now, this here is a very small number, and this doesn't really matter. So that's why in GCSE, you'll often see that equated to 0. But this is A-level, so this doesn't happen. So then we can do the exact same thing with the charges. We can see that the charge of the proton divided by the charge of a proton, 1.602 times 10 to the power of minus 19 divided by the charge of a proton, is going to equal plus 1. So I should put these pluses here. So plus 1. And then if we divide the charge of an electron with the charge of a proton, 1.602 times 10 to the power of minus 19, I never learn, put a plus, that is going to be equal to minus 1. Now, these pluses and minuses 1s are much easier to deal with than the previous 1.672 times 10 to the power of minus 27 nonsense. So we can make a new table comprised of the relative mass and the relative charge. So we can have our proton, we can have our neutron, we can have our electron. And let's draw a table. Let's do it in blue this time, with our mass and our charge. So the relative mass of a proton is 1 and its relative charge is plus 1. Let's do mass, charge, and the relative mass of a neutron, as we saw, is 1 and its charge is going to be 0. And then the relative mass of an electron is 1 over 1,836, and its charge is minus 1. So this is a much easier table to remember, but this value of an electron we don't really use that much, so committing this one to memory is a bit pointless. But these are fairly easy to remember, and will give you an understanding of the key concepts of chemistry. So, as you know, in chemistry we have different elements shown on the periodic table, which looks a bit like this thing, which kind of weird and ugly and full of boxes and full of letters that you don't know what they mean. But this is actually quite a beautiful thing. It shows us all of the different combinations of protons, neutrons and electrons that we've discovered in the world. So let's have a look at one of them. Let's have a look at carbon. Carbon is denoted by a C, so that people who don't speak English can know what they're looking at when they see this. But it has two little funny numbers next to it. It has a 12 and a 6. What do these mean? Well, 6 is the number of protons. It's called the atomic number. And the number of protons is really what makes an atom different from another atom. It gives it different properties. So the atomic number is pretty important. That's why the elements are numbered 1, 2, 3, 4, 5, 6. That's their atomic number. That's the number of protons they have. So that is equal to number of protons. But then there is this little funny number. And this funny little number is called the mass number. This is how heavy the atom is in relative mass. So if the proton and the neutron have a relative mass of 1, then the mass number must be the number of protons plus the number of neutrons. And this really isn't as important as the atomic number. It just allows us to do a lot of calculations involving amounts that we'll get onto later in the course. So you'd be forgiven for thinking that the number of protons is going to be equal to the number of neutrons. I mean, in the case of carbon it is. We can see that it has a total amount of 12 protons and neutrons, and it has 6 protons, so that means it must have 6 neutrons. So this is the neutrons, and these are the protons. These are the protons plus neutrons. So what happens then with something like chlorine? Well, chlorine has an atomic number of 17, so it has 17 protons, but its mass number is a little weird. According to the periodic table, chlorine weighs 35.5. So what's this about? Well, if we apply this like we did here, we can say that the number of protons and neutrons, 35.5, minus the number of protons, is going to equal the number of neutrons. And according to this, the number of neutrons it has is 18.5. But that means it must have half a neutron flying around. And I'm no physicist, but this would probably create a black hole or something, so that can't be true. Chlorine surely can't have half a neutron in it, and it doesn't. What is happening here then? Well, suppose that we look at 2 chlorine atoms. Here they are, chlorine and chlorine. If we measure the number of neutrons that this chlorine atom has, we'll arrive at the conclusion that it has 18 neutrons. But then if we measure this one, it'll have 20 neutrons. So then, how do we work out the mass of a chlorine atom if it has 2 different possible masses? Well, we can work out its average the average mass number. And this would be like if we get every single chlorine atom in the universe, weigh it, find out how many chlorine atoms there are, and then divide it by the number of chlorine atoms there are, we'll arrive at the conclusion that the average weight of a chlorine atom is 35.5. But how do we measure it without doing that? Because that's impractical. Well, what we end up doing is these 2 chlorine atoms have different chances of occurring naturally. This chlorine atom with 18 neutrons, and coincidentally a total mass of 35. This one having a total mass of 37 when we take into account 17 protons that it has, bringing the total mass to 35 and 37. This chlorine atom has a 75% chance of occurring, and this one has a 25% chance of occurring. So 75% of all the chlorine atoms are this chlorine 35, and a quarter of them are this chlorine 37. So then, if we get the weight times the probability of it occurring, and then add the other number of neutrons in this chlorine, so 37 times its chance of occurring, 0.25, will equal 35.5. So that's our magical conclusion, and that's why that's the way it is on the periodic table. Now, a lot of the elements on the periodic table have these weird decimal numbers for their mass numbers, and that's because a lot of the elements in the periodic table exhibit a property called isotopes. Now, isotopes are the strict definition is they have the same number of protons, but a different number of neutrons. So these isotopes will affect a lot of chemistry. They'll affect how many different weights a molecule can have. They'll affect the properties of certain things. But that's all degree level stuff. You just need to know in your A-level specification that the isotope is going to be the same number of protons but have a different number of neutrons. And this will particularly affect something that we call mass spec. But we'll get onto that later.